So hello everyone, Radhe and welcome back to my channel. Today we're discussing the LeetCode Contest 482 and we're going to discuss the first three problems of this contest. So this contest was more on easier and brute force side. So yeah, we'll begin with the first problem. You're given an integer nums of length n. We can choose an index I such that it is from 0 to n minus 1. And then for the chosen split index I, let prefix sum of I be the sum from nums of 0 to nums of I, and suffix min be the minimum value among nums plus 1 till nums of n minus 1. The score of the split at index I is defined as prefix sum of I minus suffix minimum of I. Right? And we need to return an integer denoting the maximum score over all valid split indices. So the problem is fairly straightforward itself, right? We define the score of I as score of I is defined by prefix of I plus suffix minimum of I plus 1, because that is what is mentioned in the problem, right? The suffix minimum of I is the minimum value among nums of I plus 1 all the way up to n, or to the last indices. So if I had something like 2, 1, 4 or 3, 2, then I could maintain two arrays. First is prefix sum, so I'll maintain a prefix sum over this subarray. So this is the prefix sum would look as 2, 3, 7, 10 and 12, right? I'm just maintaining a basic prefix sum. And secondly, I could maintain a suffix minimum array also. So suffix minimum of I will denote what is the minimum possible index if we iterate from the last element to the current element. So I'll begin with the last element. So this is 2, I'll set this 2. Now I'm comparing 2 and 3. So 2 is smaller, so I'll add a 2 here. Now I'm comparing 2 and 4. So this is 2 again is smaller, so I'll again add a 2 here. Now I'm comparing this 2 and 1. So 1 is smaller, so I'll add a 1. And since 1 is smaller again, so I'll add a 1 again, right? So this would be my suffix array and this would be my prefix array, right? And what the problem says is, for this is actually not plus, this is minus, my bad. So the problem says score of I is defined by prefix sum of I and then suffix minimum of I plus 1, right? So we can iterate for all the indices and then we can calculate this value, right? So for this expression I could just calculate prefix of I, because this is pre-computed, right? The prefix and suffix arrays. So I could just add up prefix of I and subtract minus suffix of I plus 1, as long as I is not the last element. If I is the last element, then we cannot use any we cannot perform this operation suffix 1. So that is why it is given in the problem that I is from 0 to n minus 1 is exclusive here, right? So n minus 1 is not included, so we'll not go till the last element, we'll only go till the second last element here. That is what is mentioned in the problem. And then I'll just maintain a maximum variable and I'll take the maximum of all such cases, right? That is pretty straightforward. I mean, if you look into the problem, we just need to maintain two arrays. One is prefix sum, another one is suffix minimum, and then I could just calculate the score as prefix of I minus suffix minimum of I plus 1, and then I could take the maximum. So that is what I'm doing here. I'm creating two arrays. I'm creating the prefix and suffix minimum arrays. So this is prefix sum array and this is suffix minimum, I'm sorry. Now I denote my score to be int minimum. Why I'm not denoting it by 0? Because the elements could be negative also, right? So that is why this whole score can be negative as well. So that is why I'm denoting this score by int minimum, right? And I'm just taking the maximum of all such cases. And that's it. This is the problem. I hope you got it. And now we'll move to the second one. Alright. So the second problem says you're given 5 integers, cost 1, cost 2, cost both, need 1 and need 2. And there are 3 types of items available. An item of type 1 cost 1 and contributes 1 unit to type 1 requirement only. an item of type 2 cost 2 and contributes 1 unit to the type 2 requirement only, and an item of type 3 cost both and contributes 1 unit to both type 1 and type 2 requirements. So you must collect enough items so that total contribution toward type 1 is at least need 1 and the total contribution towards type 2 is at least need 2. Return an integer representing the minimum possible total cost to achieve these requirements. Okay. So we have been given 5 variables. First is cost 1, then is cost 2, then we have cost both, then we have need 1, and then we have need 2. So I'll just briefly explain what this problem says. So we have been given some costs associated with some item, right? So let's say this is the first type of item and this is the second type of item, okay? So I need to purchase this need 1 number of items, the first items. I need to purchase actually the first item need 1 times. So if this was 5, then I need to purchase the first item 5 times, alright? Similarly, if this was 10, then I need to purchase the second item 10 number of times, alright? And now what I can say is, in order to purchase these need 1 or the first item, I need to pay a cost of cost 1, right? By paying the cost 1, I could purchase 1 item from need 1 or 1 item of the type or of type 1, right? So this is the cost of cost 1 is associated with need 1, right? So let's call it X for now. Similarly, the cost of 2 is associated with need 2, right? So in order to buy the second element or the second item, I would need to pay the price of cost 2, right? So okay, there's one more thing, that the cost both actually is something like, let's call this Z for now. So if I use this cost both, so if I spend Z money or Z rupees, then I could buy one and the first and second item simultaneously, right? So I do if I pay a cost of cost 1, then I could only buy the first item. If I pay a cost of cost 2, then I could only buy the second item. But if I pay a cost of cost both, then I could buy both the items, the first one and the second one also, right? So this is what is mentioned in the problem. Now we need to purchase the need 1 first items and need 2 second items, and we need to calculate the smallest possible cost for purchasing these items. Okay, so now I'll break this down into some cases, right? First one is that let cost 1 be 1, cost both be something like 100, and we need to buy 10 items of need 1 or 10 items of first type and 20 items of second type. Okay, so initially what I can think of is, I'll just take this cost 1, I'll multiply this by need 1, and I could I can calculate what is the total cost of buying need 1 items. So this is essentially cost 1 into need 1. And then similarly, we also need to buy the second type of item, right? So cost 2 is associated with the second type of operation or second type of item, sorry. So I'll multiply cost 2 into need 2. This will be need 1. I made a mistake here. This would be need 1. So this is one obvious way, that I could pay a cost 1 to buy all of the need 1 items, then I could pay a cost 2 to buy all of the items of need 2, and then this is my final answer, right? Because what I need to do in the end is just buy the first type of item need 1 number of times and buy the second type of item need 2 number of times. So this is essentially the basic math formula, right? If one item cost 1 rupees, then how many or how much cost does need 1 operation or need 1 items cost? So this is essentially need 1 into cost 1, right? Now the second case could look as, if I take some example, this was first case, I'll just move this down below, right? So this is easier to see. Now the second case could look as this is maybe 100 cost 1, the cost 2 is 100 again, and the cost both is 1, and I again need to buy 10 items of the first type and the second, and 20 operation or 20 items of the second type. Now you can see that cost 1 and cost 2 are very high here, that is 100 and 100, right? This is actually very high. So what would be a smarter move here? I think the smarter move would be to use this cost both, because by using this cost both I can buy the first item also and the second item also at the same time, right? So what is the total cost if I choose to buy cost both, or if I choose to pay cost both price in order to buy both the elements? So that would be nothing but cost both into maximum of need 1 and need 2. Now why is that a maximum here? That is because if I need to buy 10 items of first type and 20 items of the second type, then I would need to pay price for 20 items, right, in total, because I can buy these items at the same time. So this will decrement by what? This is 10, 20. So first I pay a cost to both, and then I buy one item of each type. So this becomes 9 and 19. Then it becomes 8 and 18. Similarly 7 and 17. So on. This becomes 0 and a 10 after buying 10 items. Then I can again buy 10 items in order to reduce this to 0, because, right, we need to reduce this to 0 as well, right, in order to buy the need 1 items and need 2 items. So this will again take 10 operations in order to become 0 and 0. So this is what? Nothing but maximum of 10 and 20. So I could take the maximum of 10 and 20 and then multiply this by cost both. So this is the second type of case that we might need to consider. Then there is the third type of case where, alright, so I actually might need to think about this for a while. So I'll just write some random values here. This is 20, this is 50, and this is 30. Or not, this is, let's say, this is 30. This is 3 and this is 5. Yeah, this is a good example. So now the third case is, because there would be 3 cases for solving this problem. We have already discussed the first 2. Now the final case is that now you will see that the cost 1 is 20 and cost 2 is 50, right? And what is cost both? Cost both lies between cost 1 and cost 2, that is 30. So it is bigger than cost 1 and lesser than cost 2, right? Right. So what I can do here is that, or I think I made a mistake. Okay, let's just continue discussing. If I encounter something, then we'll go from there. So it might happen that this cost both lies between cost 1 and cost 2. So for some operations we might need one of these cost 1 or cost 2, and for the other thing we might need this cost both, right? This might also happen. So I choose cost both and take the minimum of need 1 and need 2 and use cost both to buy those items, right? So if I take the minimum of 3 and 5, this would be 3, and I could or let's swap these values, then it would be much more clearer, I guess. Just a minute, I'm sorry for the trouble. I haven't actually thought of cases beforehand. I probably should have. Yeah, so this is a good example now. So now what I can see is that this cost both is lesser than this cost 1, right? Right? So what I can do here is that for buying this cost 1, or for buying this first type of operation, first type of item, I'm sorry, I could use this cost both, right? And for buying the rest of the remaining items of second type, I could use the cost 2, because cost 2 is lesser than this cost both, and cost both is lesser than this cost 1. So if I'm saying that whatever is the minimum value of need 1 and need 2, I can choose to buy that with cost both. So for 3 and 5, I can choose to buy the first type of item with cost both. So it will now be 30 into 3. Then I have bought 3 items with cost both. That means my both of the items have been decreased by 3. So this would have become 0 and this would have become 2, right? So now we have 2 remaining, and now we can buy this 2 by using this cost 2, because if I buy this with cost both, then this 30 is bigger than 20, right? So this will increase the cost, so I could use this cost 2. So now this would be 20 into 2, because 2 were remaining, and this is the minimum possible answer for this case, which is 90 plus 40. So this is 130, I guess. Yup, this is 130, right? So this also can happen, because if we would have taken the maximum of these both of these, then we would have just used this case, right? So there could also be one possibility also, that this cost both lies between this cost 1 and cost 2, right? So I can choose to buy with cost both for the item which is of higher cost than cost both, right? So this 50 is greater than cost both, so I can use this cost both to buy this 50 or this first item. So I buy this first item. So I have bought 3 items of the type of the first type and the second type as well. So I'll do what? I'll do a need 2 minus need 1, right? And then whatever is remaining now, this is 2 remaining, right? So I can use this cost 2 to buy this need 2, right? And that is it. So we can take the minimum of all these 3 cases. So this is what I can use this cost both to buy the minimum of need 1 and need 2. Plus, so whichever was maximum, so this was need 2 which was maximum, so I'll do a need 2 minus need 1. So these are the number of items which are remaining. I could do a cost 2 here. I can do it in such a way that I can always maintain this need 1 to be minimum, right? So if we encounter something like 10 and a 5, then I will just swap these things, right? I will just swap these places. So now this need 1 becomes need 2, so this is 10, and this need 2 becomes need 5. Also we'll swap their costs as well, right? Because otherwise the answer would be different. So I will need to swap these costs as well if need 2 is greater than need 1. Or I'm sorry, if need 1 is greater than need 2. So I'm basically maintaining my need 1 to be smaller than that of need 2, right? So that is what essentially I'm doing. And we can now calculate this value. And this is, we can take the minimum for all 3 cases. And that is my final answer. So if you will try to prove this, there wouldn't exist any other case. At least I have tried to prove this. And this is the final answer. This is the final code. So I'm first taking the cost both into maximum. So I'm buying all the items with cost both. Then if my need 1 is greater than need 2, so I'm just swapping the need 1, need 2 and cost 1, cost 2 in order to maintain need 1 is always lesser than equals to need 2, right? And now I could do a need 2 minus need 1. This will always be positive now because need 2 is greater than need 1. And then cost 2 is the cost associated with the one which is greater, right? So this always works. And then I could take the cost both for the one which is minimum, which is need 1, right? And the third case could be I take this one actually. I take the cost 1 for the need 1 item or the first item and cost 2 for the second item, and I could take the minimum of all 3 cases, and that's it. So now I hope you got this problem. Now we'll try to move on to the third one. Okay. The code is very straightforward. The problem also is fairly straightforward. I will just try to break this down. So given a positive integer k, find the smallest integer n divisible by k that consists of only the digit 1 in its decimal representation. Example 1, 1, 1, 1, and so on. Return an integer denoting the number of digits in the decimal representation of n. If no such n exists, return -1. So this problem says that we have been given an integer k, and then we can have values as 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. And then we need to find what is the minimum number of digits, what is that number with all the ones, essentially with the minimum number of digits that is divisible by this k, right? So we need to find the multiple of this k here. So if this was k was 11, so this would be 11 for this one, right? If k was 7, then I think this 111 is divisible by 7, the first number which is divisible by 7. So we need to find the first number which is divisible by 7. So this had 3 digits, so I'll return a 3 here, right? So we need to do this. So the brute force solution will actually cause is actually, I think, very stupid, because this can grow very rapidly. K is up to 1e5, right? So its multiple can grow, very rapidly, very quickly. So if an answer consisted of let's say 30 or 32 digits in its representation, that is 32 times, so this will never fit in any integer or anything long or anything like that. So this is not a good idea to use some kind of data type to store the value and then try to brute force. There is another technique, if you know about it, that is modular arithmetic, which says if I multiply a by b under some modulo x, this essentially is nothing but a modulo x into b modulo x whole modulo x. So I'm saying that if my k was 7, so if this 111 was divisible by 7, then if I keep on maintaining I only maintain a remainder of k, then that is pretty sufficient, I would say. So I'll just try to run on a sample here, and just let me make sure that 1 was divisible by 7. Oh, so no, it is not. So I'll take another example. So 1 6 times is divisible by 7. Alright, so 1 6 times is divisible by 7. 1 1 1 1 1 1. Alright. So k is 7. Right. Yup. So now I take this one, I take this modulo of 7. So 1 mod 7 is 7 itself, which is 1. I'll just write the remainder here. So this is 1 itself. So which is not 0. That means that this is not divisible by 7. Now 11 mod 7 is 4, which is again not divisible by 7. If it would have been divisible by 7, then the remainder would have been 0, right? So I'm saying that whenever I'll encounter a multiple of k, then I will encounter a remainder of 0, right? And as soon as I encounter a remainder of 0, then I can break out of this loop and I could return the number of digits that I'm currently on. So I can basically iterate on the number of digits, and I could take the modulo so that the length do not grow rapidly, right? The length remains between 0 to k minus 1, and k is from 0 to 1e5, right? So this condition always holds. Now 111 modulo 7, so we might want to do this here. 111 modulo 7, this is 6, so now we have 6 over here. Now we have 1111 modulo 7, so 1111 modulo, where is modulo? Yeah, modulo 7. What is that? Wait a minute. 1111. Achha, this is percent. So where is this modulo? So I think this is finding out the percentage, and I don't see a modulo here, so I'll just Google this 1111. Which was that? Yeah, 1111 modulo 7. This is 5 now, so I'll write a 5 here. Now this is one more one. This is now 2, so I'll do a 2. I'll do a 2 here. Now I'll do 1111 modulo 7, which is I think 0. So this is 0. Now to prove a solution for this, I'll take one example like this. So this is 1 2 3 4 5 6 7. So now we have a number like this, right? So what happens when I modulate this by 7? Now this is 1 again. Now I do 1 8 times. So just stick with me, you'll know why I'm doing this. So 1 8 times is 1 1 1 1 1 1 1 1. So this is 2, or this was what? 4, I think. Yeah, 4. So you'll see here, you can see here that the values are repeating after this 146520. Now the values are repeating again. Now I'll show you guys a very interesting example. Okay, so now 1 modulo 7 was 1. Okay, and now I multiply this by 10 and add a 1 here, because that is the only possible way I could make 11. I could make 11 and then 1 1 1, right? So to go from 1 to 11, I'll have to multiply this by 10 and add a 1, right? So to go from 11 to 1 1 1, I'll need to multiply a 10 and add a 1. Similarly, if I'll have to go from 1 1 1 to 1 1 1 1, I'll have to add, multiply this by 10 and add a 1. You get the idea? So now I'm actually not doing this on the number itself, because this can grow very rapidly in the size, in the number of digits. I'll actually do this in modulo. So 1 modulo 7 is 1 itself. Alright, now 1 into 10 plus 1 mod 7 is what? This is 10 plus 1 is 11. 11 mod 7 is 4. So this is 4. Okay, now what? Now I take 4 into 10 plus 1 modulo 7. So this is what? 41 mod 7. So 7 5s are 35 and 6 is remaining, so this is 6. Now I do 6 into 10 plus 1, which is 61 modulo 7. So 7, I think 7 9 is 63 and 7 8 is a 56. So 56 and 61, 5 is remaining, so I get a 5 here. So you'll see here that my values are the same, right? No matter if I perform the modulo on this operation or on this number on the modulo itself, because by modulo arithmetic, no matter if I perform the operation on the original element or on the remainder, the answer remains same. The values will remain same here. That is what I'm saying. So you do not actually have to maintain this big number, right? Because this can grow very rapidly. This could be 1 1 1 1, let's say 100 times. So then what you'll do? There's no language in the world that could store that big of a number, right? So you have to actually implement this smartly, because the modulo arithmetic says that a into b modulo x is the same as a modulo x into b modulo x whole modulo x. So it doesn't matter if I modulo on this whole number, or if I modulo on this big number multiplied by 10 and add a 1 here, because that is what I was doing in this one. So I could do the same in the previous remainder. So if I got the previous remainder as 5, I could just multiply that by 10 and add a 1 and then take the modulo out of 7. So this is 51 and 51, 7 7s are 49. So I get a difference of 2. So I'll get a difference of 2 here, or the remainder of 2 here. So I hope you got the solution of how actually we are handling these large elements. Now the thing is that why the values will start repeating is because the nature of modulo. That means if I have some number k, so it can only have remainder from 0 to k minus 1, right? if we would have encountered a number k, then the k modulo k is 0 again. So then it will go from 0. And then if I had a k plus 1, then k plus 1 modulo k. So k plus 1 modulo k is nothing but 1 itself, because if you can open this modulo, so this is k mod k plus 1 mod k. So this is 0 and this is 1 mod k. So this is 1 itself, right? So I'm saying the values will start repeating. There are only k possible there are only k possibilities for any number, right? So k only have k or what can I say? A number k only have k different or k distinct remainders, right? From 0 to k minus 1. If I had a k equals to 7, then I could get remainders as 0, 1, 2, 3, 4 and 5 and 6, right? And similarly, if I encounter a 7, this cycles begin again. So this is nothing but a cycle, right? And I'm saying that when you start performing this operation again, when you encounter this element again, so when you will do it into 10 plus 1 here again, so the value will start repeating, right? After k operations, the value have to start repeating, because essentially you did a 1 into 10 plus 1 here, and you did a 1 into 10 plus here. So this is the same thing, 11 and 11. Modulo k is modulo 7 is 4. So this will again start repeating. Now you do a 4 into 10 plus 1, which is 41. Modulo 7 is 6. So you'll again get a 6. So these values are actually getting repeated here. So that is only what I'm saying, that for any number k, I have only k distinct remainders, right? Other than that, I do not have any remainder. I hope you got it. So I could just iterate from 1 to k and then calculate all the possible remainders. If I encounter a 0, as soon as I encounter a 0, I'll return the number of digits that I'm currently on, right? And if I do not encounter a k while iterating from 1 to k, that means I have encountered a cycle and I will never encounter a 0 again, right? So if the cycle would have been something like 1, 2, 3, 4, 5, and then again 1, 2, 3, 4, 5. So you agree that we will never encounter a 0 again, right? If our cycle is going something like that. So in that case, I could just print a minus 1 here. So that is what I'm doing here. I'm iterating from 1 to k. These are actually the number of digits here. So I'm maintaining a x. I'm multiplying this by 10, adding a 1, taking the modulo. If this modulo becomes 0, I'll just return the number of digits I'm currently on. If after performing all the k iterations, I do not encounter any remainder 0, that means I have entered a cycle and I will never get a remainder of 0. In that case, I'll return a minus 1. And that is all for this problem. The proof was very important mathematically. This can come handy in a lot of problems actually. So I hope you got it. And I hope I was able to explain these problems to you in a good manner. And let me know in the comments what do you guys think that about these problems and how well you did in this contest. Again, thank you so much for watching, and I will from next time I will try to cover all the 4 problems. I actually solved the 4th problem after the contest. It was something related to digit DP. I wasn't very comfortable with digit DP, but from the next time I will try to bring all the 4 problems to you. But anyways, I hope you got it. If someone is watching, please let me know, and thank you so much for watching, and Radhe Radhe.